Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I have a course that I'm teaching on machine learning. And I've recorded every one of the lectures, put them online. If you're just jumping in now, I invite you to look at the entire series. We've gotten pretty far. We've gone through a lot of material and content. And recently we got into tree-based methodologies, decision trees. We went from there to ensemble methods like tree bagging, random forest. And now to finish off, we'll talk about gradient boosting with trees, tree gradient boosting. So let's get into it. What's the motivation here? Well, there's a great opportunity here to further expand on the concept of ensemble-based learning methodologies, the idea of combining multiple estimators together in order to get a more robust estimate with machine learning. Very powerful stuff. But what's really cool here with the gradient boosting, we have an opportunity to combine in the concept of gradient descent optimization, which is very powerful. And these methods are competitive. Whereas decision trees were actually quite weak, these methodologies are getting to be more cutting edge and competitive with the most up-to-date machine learning methodologies. So let's get into it right now. So decision tree review, we've got to do this. Not a big deal. We've already had a lecture on decision trees. We've covered all of this, but just to recap really quickly, the fundamental idea is to divide the predictor feature space into mutually exclusive exhaustive regions. Mutually exclusive meaning that they don't overlap with each other. At every single value of combination of predictor features, you only belong to one region, but they're exhaustive meaning there's no gaps. In other words, there's always a region. You're never in a void between regions. And then what we'll do is for every observation to make a prediction for the continuous case of prediction regression, we'll just take the average of the training data within the region. And for the categorical, we'll do something like majority rule. Okay, so not a big deal. Simple segmentation of the predictor feature space to make predictions. Well, how do you construct them? They're going to be, we'll use hierarchical binary segmentation. We'll start with everything in one region, it's top down, and we'll find the best possible split, and then we'll keep finding the next best possible split, only making splits on one feature at a time within a single region. And the result is we get this type of a set of nested decision gates. Turn it upside down, it looks like a tree. That's the whole idea of decision tree. Now we could keep splitting and splitting and splitting until every single training data are in their own regions, and that would of course be overfit. Typical approach is to apply some type of reasonable minimum number of training data per region. The idea is you have to infer a category, most likely category, or a average for a continuous regression model in every single one of those regions. So you really do need more than one data to do that. So we could try to do some type of minimum RSS reduction, residual sum of square reduction, as a hurdle, but that typically doesn't go very well because you might not have a great split right now as far as reducing error, but maybe it will enable a future split that actually has a big jump. There's no reason to believe it's monotonic relationship between the error reduction and the order of the splits. So what's it look like? We build a tree. Here's a really nice example. The tree has porosity and brittleness, a geomechanical type of property from the subsurface, and we're making predictions of a fluid production rate when wells are drilled. Could be water, could be oil, could be anything. And so the really cool thing about RStudio is when you look at the trees, you can see that the length of these branches is proportional to the error reduction from making that split. And you can see immediately that these early decisions have a huge impact. The later ones are kind of not having too much impact, and we can make a decision about pruning. Here's showing the 12 regions that were assigned, those leaves on the end of each one of those decisions, and their boundaries and the estimates within each one of those regions. So that's pretty useful. We can see that. And of course, we'll do some type of pruning, hyperparameter tuning. You make a decision about what's the best level of complexity for your tree by simply just doing a plot. This is a k-fold cross-validation here where we have the error in k-fold cross-validation averaged over all the folds versus the number of nodes in the tree. And we can look at that plot and make a decision about what's the best level of complexity? Are we going to take some acceptable level of error? We don't see it coming back up, so don't really think we're getting overfit necessarily. The rate of improvement, we might look at that and say, well, you have diminishing returns, complexity is cost, and so at some point it's not worthwhile adding more splits. Now we're going to have some type of training and testing associated with this. We just showed the example of k-fold cross-validation, but that's always important to differentiate the idea of training the model parameters, those split locations, and tuning in the testing phase the hyperparameters, the degree of complexity of the tree. And we've talked about that so many times. Let's go ahead and extend this to boosting. Let's introduce the concept of boosting in the specific case of boosting trees. We'll comment that this could be completely general, i.e. while we explain this for decision trees, in fact boosting could be applied to really almost any type of machine learning methodology. And so what's the idea? We're going to build a model sequentially. The next model is going to be dependent on the previous model. So they're building on top of each other. They're not independent estimators like we did with tree bagging. Now, if we compare bagging and boosting, bagging uses bootstrap versions of the data to build multiple estimators and averages the estimates to reduce model variance. It's all about attacking model variance, trying to get that down, because that's the real big impact as far as the model accuracy. Boosting uses a modified version of the data, in other words, the residual of the data, to slowly learn to reduce model variance. It becomes more robust because it's learning slowly, incrementally. Also, boosting does not use bootstrap. There's no attempt to try to get multiple representations or realizations of the data. Okay, so what's the general workflow? We're going to build a weak predictor model. In fact, imagine a model that's dramatically underfit. I'll mention it later. The model could be barely better in random. Okay? It has a high degree of error. We calculate the residual of the error at the training data. We update the training data with that residual, and now we repeat. Build a weak predictor on that residual, calculate the second residual, update the training data, which was residual, with second residual. Now build a weak predictor on the second residual. Calculate the residual error, which is now the third residual, and continue, continue, continue. So this is really interesting. We're going to build a simple model to start off that has a very high error rate. We'll call it a weak predictor. The model may be only marginally better than a random model. So this is what we'll do. We'll fit the data with a weak predictor. We're going to have our predictor features x1 through xm, and y is going to be our weak predictor of the response feature that we want to work with. Okay, so far so good. Then we're going to calculate the residual with the training data. So we got the true values, we got the prediction values, so HK is going to simply be the residual at the training data locations. Now remember that FK hat is a weak predictor, so this is going to be a substantial amount of error. Okay, there could still be all kinds of structure in it. It's not going to be like we've seen before where we fit a lot of the signal and the result may actually be, in many cases, we're assuming it's going to be random error. Nope, we're going to have structured correlated error. And so there'll be something else we can fit. With every step, we'll keep fitting it. Then we'll be able to fit another weak learner. Now this time, notice it's being applied to that error. So we're fitting the residual from that first model with another weak learner. Isn't that cool? So we're building the model sequentially. It kind of reminds me of that, the shaving commercials. I don't know, it was a long time ago, where they talked about the first blade got incredibly close, the second even closer, the third. This idea that the first model goes through and does not a great job, but it gets something. And then the remainder, the next model gets some of that, and the next one gets some of that. So kind of that idea. I think it's really, really powerful. Now we calculate a second residual with the training data. So look at, now we're taking the residual, which is kind of cool. And the result is that we can now fit a third model to the second residual. And we'll keep going until we reach a point where we're comfortable with the model. Now, so the approach is to model, calculate a residual, model the residual, repeat. And if you think about it, that's an additive model. In fact, the ultimate estimate that we're making is simply going to be the summation of all of those models. So this is really cool. So it's a very simple model. We have a bunch of weak learners that are building on top of each other, but the actual estimate we make in the end is just a summation of all of those learners. Okay, so that's really cool. Whereas before with tree bagging and random forest, we were taking an average of the estimators. Here it's an additive model. We're taking the summation of the estimators. Now there's a variety of methods that could be applied to boosting. In fact, what's really interesting is that people will design the model such that they are mixing and matching different models because they want to capture certain, almost like spatial temporal frequencies of the problem. For instance, a polynomial regression model could capture really nice long-range trends or features from the model, and then you would apply some other type of methodology like decision tree to capture maybe the more short scale, the more noisy, kind of smaller scale details. And so if you think about it, that would be a very hierarchical model where we're capturing different scales with different models, and it's all additive. So this does have a nice analogy to everything we talked about before about trend modeling and residuals. Okay, let's give ourselves a really simple model example. I want it to work in one predictor feature and one response feature so we can really visualize what the model's doing. Because this is a little bit complicated, I want to make sure people can catch on to this. So we go ahead, we have our data available to us. It's irregular, it's got some noise in it, it's highly nonlinear. Okay, so let's go ahead and we're going to work with decision trees. But they're only one level of trees. That's called a stump tree. Only one decision at a time. Okay, so let's start with a weak predictor. It's going to be weak because it's a stump. That's a very simple predictor. We got one level. We go through and we look for the very best split to make in this data set. So the current model, we determine this split. There's a little bit of a slope here. That's because of the discretization of the problem. I should have probably made it more fine scale. This should be a vertical line right here, just in case you're wondering. Okay, because it's just a threshold in the predictor feature, right? Okay, so this was the very best split. You take the average of this, you take the average of this. That's our good model. That's our weak estimator. And now you can calculate the residual. Now look really closely what happened. Basically, when we went to residual, now imagine all of the values here are just simply the difference between the model, between the true values of the training data and the model. And so up to here, it really does look kind of very similar. It's all centered around this line. Just imagine this line moved down to here. And now we jump up here, and this part here is like centered here, but then it's all shifted down. Look at this training data point right here. Shift it down to be just below because the delta here, and the delta here, it's larger, so it's just a little bit below. Okay, so that's a residual right there. Okay, so what are we going to do next? We got to fit that residual. So just to keep track of this, this is what we're fitting. We're fitting this residual right here. If we look right here, right there, that residual is now the residual that we're fitting with the model. And this is the very best next split, the stump decision tree. And if you look over here, this in fact is the delta from this model right here. Now this is really cool because what you can see is that in locations where it's going low, it's shifting the values up higher. In locations where it's going high, it's shifting the values down lower. So it's really kind of interesting the way it's being applied to the training data across the whole range of the training data, right? This model, these incremental models are additive over the whole range of the predictor feature. It's not just additive over a specific subset. It impacts all of the training data residuals, and that's important to remember. Now over here, what I'm doing is I'm keeping track of what's the additive model. If I took model 1 plus model 2, this is where we got. So let's go back. That's where we were originally. Then with this new model, let's go back and forth a bit. We took this part of the model and we shifted it lower, and we took this part and popped it up. You see that? Isn't that cool? Because that additive model is being applied over the whole range. It's causing a negative effect on this side, a positive effect on this side, and here's the new residuals. Okay, let's do it one more time. So then this is the residual. If you look here, this plot of residuals, it goes over here. Now we fit that with the third weak estimator. And we get this model right here. And you can very quickly see that this is the residuals here from this line. So here's the new residuals going forward. And the model, look at what we did. We put a little bit of we popped this side up right here, and this side dropped down a little bit. You see that? Kind of cool, right? Okay, so once again, this side from here to here pops up. This side from here to here drops down. You see that? Because of that new additive function. And here's the new residuals. Well, we can keep going until the cows come back home and just keep adding these models together. What does it look like if we go ahead and just look at the whole thing all at once? First additive model, second, third, fifth, sixth, seventh, ninth, 10th, 12th. We're slowly converging on fitting the data better and better by doing this with the boosting, by fitting the residuals sequentially over and over again. Now this is kind of fun. We can look at the actual residuals and the models. So if we go ahead and we look at the residuals, what we can see is over time, residual, 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 residual. You can see how the residuals are dropping, the models being fit. Now don't be confused, there's a couple steps in some of these. In some of them I'm showing two additive models at once. I kind of jumped from the third to the fifth, so I showed the fourth and the fifth together. I showed the 8th and the 9th together. It's just the way I discretized the problem. But look at the residuals are slowly dropping over time. So this is really cool. This is really a neat way to model this problem. Okay, let's make some comments around it. Boosting is another strategy to improve model accuracy while avoiding overfit. A complicated model will fit the data with the potential for overfit. A boosting model learns slowly with very simple, weak learners. It avoids overfit. It's a form of sequential learning. Okay, and let's go ahead and show another, and this one's more of a schematic example to further illustrate this idea of sequential learning. Okay, so this example is adapted from this blog post right here. Appreciation for the blog post. Actually, a really nice explanation. Appreciated that. So what are we going to do is you look at this. We have predictor feature 1 and 2, and we have training data shown by the symbols. Now, the training data, if it's a plus symbol, it means it's high. It's a 0 or a circle, it means it's low. And the size of the symbol tells us how high or how low. Small symbols are very little, negative or positives. Large symbols are large values. Okay, so what we can do is we can go and fit our first stump tree, our first weak predictor. Now, what we see here is that there's these two high values right here. I can capture them by putting a split right here. And you can imagine the prediction would be higher there and lower everywhere else. When I do that, what happens is you notice that these symbols get smaller because I've captured that and I brought it down. But these plus symbols go larger because they were all part of the region which was predicted with a small value. But the circles get smaller because I'm actually capturing that lowness of those values. You see, this is really cool, right? We're kind of learning the patterns of the problem. Now the next split is over here. We can capture these two circles all at once. And when we do that, what happens is that those circles go very small. We've really captured the low values there. These circles went a little bit larger because we were saying, oh, those values are going to be higher there, but those values actually were low. These plus symbols all go smaller because we captured the high side of those values. Okay, and then we could just keep going and going and going. And so by building these additive models that are indicating low, high, different subsets and regions, we're slowly capturing the general magnitude of the values at all locations. But remember, each one of the weak predictor models are over the entire model. And so they're sequentially updating the data at all locations. The residuals keep updating, but we keep learning and fitting those patterns. Okay, now what I'm going to do now is I'm going to stop this video right now, and I'll have a separate video where I'll get into the concept of extending boosting to gradient boosting from the standpoint of like a gradient optimization. All right, as always, I hope these videos are helpful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I teach in data analytics, machine learning, and what else? Geostatistics. I teach a lot of geoscientists, general scientists, some biologists, everybody basically, and petroleum engineers and other types of engineers. And it is my pleasure to share everything I teach within the university system online for anybody who wants to join in. I heard recently that there was a high school that retweeted about my courses. And so if you're in high school, hey, enjoy the courses. This is university. This is what we do in university. There's no mystery. We're demystifying machine learning. We're demystifying engineering in university. And if you like what you see, come join us. Become an engineer, become a geoscientist, become any type of scientist. Go to school. It's awesome. It's quite a journey. All right. Hey, everyone, take care. Have a good one.